Welcome to the beginning of the second week of the IAP course on cold fusion at MIT, run by Professor Hagelstein. And I will present over the next 2 days experimental results that we have found over 24 years in cold fusion. And it does have utility, and it is real. And what I will try to do in this introduction is cover very loosely as many aspects of what we've uncovered as I can. For example, we'll talk about, I use the term lattice-assisted nuclear reactions, LANR. We'll talk about the materials. We'll talk about how we calibrate the calorimetry. I'll give you an introduction to the production of excess energy. Then we'll take a break and talk about some engineering details dealing with deuteron flux, metamaterials. We'll come back to excess energy, talk about heat after death and how to control it and other things we've learned from the electrical engineering control of cold fusion. Then we'll talk about near-infrared emissions, electricity production, and hopefully we'll get through as much of this today. And then we'll start on nanomaterials tomorrow and then summarize. And hopefully when you're done, you'll understand why we get such a gain from making the cathodes into metamaterials. You'll understand how we get a phenomenal gain by dealing with optimal operating points. And even we get some control by controlling heat after death. And that's heat after death refers to the fact that when we have an active cold fusion cell and we get it primed and the excess energy coming out, and sometimes as we take off our input energy and input power, we continue to get excess energy coming out for a while. That's called heat after death. And when we use calibrated calorimetry, we call that cherry technology data analysis, and you'll learn how to do it. But first, I want to talk about the materials for those that missed Peter's very erudite discussion last week as best I can. The reason we need cold fusion is the fact we don't have it now. We depend on fossil fuels, and we all know what the problem is there. We're wasting a finite ancient resource, and it does nothing but create pollution, large amounts, trade imbalance, economic upheavals, and instability, as we can see by just picking up the newspaper. We know that there's serious effects on health in the U.S. right now. In Utah, it's a major issue. And we could make all of this go away with cold fusion. How bad is it? It's this bad. For every gigawatt per day, that's a power rate times time that a city needs. Boston, I think, runs about 6 gigawatts to run. Per day, you're burning 9,000 tons of coal per gigawatt, and each one of those makes 30,000 tons of CO2, 600 tons of sulfur dioxide, 80 tons of nitrogen dioxide, yada, yada, yada. And these obviously are things we could avoid if we had a working cold fusion system, because the same amount of power could be generated by just converting 4 pounds of heavy water to helium. Nuclear energy obviously is very helpful, but occasionally things don't go quite as we planned. For example, in Fukushima, this was a picture from Chernobyl. It was released yesterday. It's turned into a vast, wonderful animal wilderness. There are other ways of making energy, hydroelectric and photovoltaic, as you know, but the problem there is you have an irregular or irregularly irregular driving force. And for those who can get geothermal or fluid flow, like some of our friends here, it's good, but it's not available for everybody. So what do we do? One alternative is we need an incredible amount of energy. These are the ways we're doing it now. The majority is with petroleum burning and coal. How can we take you who are in the audience to learn some of these science and engineering techniques and convert us to a cold fusion economy with a distributed system? Hot fusion has a long history of failure. When I first came to MIT in 1966, I thought I would work on hot fusion, and they promised that we would have it by 40 to 50 years, which is about the same time limit we have now for seeing it. So clearly there were problems there. And for those who've worked in cold fusion, one of the things we've learned is to get a really well-working system takes a lot of experiments. I don't think hot fusion is going to work the first time they do it. So the problem is you're going to have a reactor full of tritium, which is now radioactive, and what do you then do? So the light at the end of the tunnel, as I see it, is cold fusion. It's non-radioactive. It has zero carbon footprint. And what can we do is figure out how to build it more efficiently and then scale up so we have a distributed energy system that can change everything. So what is cold fusion? What is lattice-assisted nuclear reaction? What we do is we take a group 8 metal like palladium or occasionally nickel. We load it with hydrogen, make an alloy from it, and we get out, once we load and achieve other difficult to achieve aspects, we get out what's called excess heat or excess energy. And what we find is that the amount of excess energy that comes out, as Peter showed you last week, is commensurate with the amount of helium-4 that we make. This is our product. So we find the helium-4 production is in quantitative agreement with Miles' case and SRI, as Peter pointed out, for production, and by rate to the Gauzy experiments. And the reason that cold fusion will turn out to be so useful is that we're getting out at E equals mc squared. The advantage is we can decrease our reliance on foreign sources. We get these incredible emission benefits, as I pointed out, where we're not making these gases that are polluting everywhere. And in addition, we are not even making CO2. So we eliminate the greenhouse problem. Now, the reason it's so useful is the fact that if we look at the amount of energy that comes out, and this is a log plot here for various things. When we eat food, we get this much energy out from butter and donuts. If we light off a bit of TNT, we get this much energy out. But the fact is, we get orders and orders of more magnitude out for the same amount of mass, as we're talking energy density, with nuclear systems, with cold fusion, and the theoretical limits up here. And that's why the sun works. So the reason that cold fusion is important is, one, it's incredibly efficient, as well as clean. Two, the fuel is everywhere. 1 in every 6,000 hydrogen atoms in water is deuterium. And if you take it out, we can then put that into our cold fusion reactor and make de novo helium-4 for powering. So here's a big source of fuel. Not many things are as clean as I showed you, because we do not make a significant amount of radiation, and nor do we make these other polluting materials. So the take-home point is we have a new, clean, efficient energy production system with zero carbon footprint. Any questions? If you have any, feel free to interrupt. Let's talk a little about the materials. As I mentioned, we use group 8 metals that we load, that means fill, like water fills into a sponge, with hydrogen, either protium or deuterium, that's heavy hydrogen. And the problem we find is that when we load it, we don't want to create cracks in the material, because then these materials come out and we don't get the sufficient loading. Water's everywhere. What we deal with when we load with an electric field intensity is, here's our water lattice, here's our lattice of the loaded palladium. These are the palladium, these are the deuterium in here. The deuterium comes from the heavy water. And what's interesting is you've all been taught that there's a Debye spectra. It's actually a little bit more complicated. When we have a water molecule, we have the oxygen nuclei at the center of a tetrahedron. We've got the 2 protons or deuterons out at the side. And when we put on an electric field intensity, what actually happens is we get intra molecular proton transfer that drifts towards the cathode and creates a cathode fall. Very few people are aware of this, and this was actually uncovered upstairs in the Laboratory of Insulation Research by Arthur von Hippel when I first came here in the 60s. And if you plot the top of these Debye spectra, which is here, it turns out water and ice are much more complicated than normally thought. And there's a whole subject we could talk about that. But they are complicated materials, and these are the ones that we use. This is actually me upstairs back in '67 looking at water, and those who've been to our lab don't see much difference. We're actually using the same similar techniques we use now with cold fusion systems that we initially used back to look at water and doped water with ammonia and sodium back in the 60s. Now the material itself, the palladium, what's happening in the field of cold fusion is that we find that it is a very complicated material. Even when you think of it as being a metal, after you run the experiments, we get these pits, we get changes, and if you read the different papers from Wars and from Mitsubishi, this, by the way, is a constructed cathode that they use in order to get increased amounts of transmutation. There's a lot of physics here in the material. Palladium. This is what happens in pure palladium. This is a spectrum that Peter Hadelstein and I took back in, I guess, '95, where we had an unloaded piece of palladium, and you see it's well crystallized over a large area, and as soon as you put the deuterium in, you change it. And what we ended up getting is a large polycrystalline mass with a crystal size of about 19 to 23 nanometers. So we put the material in, it changes the palladium. We don't want it to change too much, we don't want cracks, but if we do it right, as I will show you, we get the excess energy out. Now, one other thing I want you to think about is there are different regions in the palladium. There's a deep region inside the metal. There's a superficial region where we see a lot of changes, for example, in transmutation, where the helium is observed. And then there's a region outside that we create by co-deposition and other methods that is a de novo material as we form. And we'll just skip over that. I just want you to know that these exist. And what may be occurring is within these regions we have a lot of active sites, and they add up. Each of them contribute over the area and the depth. And from that, from these multiple sites that we have activated, that's what we see macroscopically as the excess energy coming out. And we'll talk more about that later. The other reason that we think that there's multiple sites involved is when we look at heat after death. For example, here we're looking as a function of time, and I'll come back to this later, and we're looking at the power output, where our output here is 1 watt. This is after the power source is taken off, we're still getting energy out. And we see, for example, that there's different time constants, and eventually there will be more analysis on this, and we can see that there's different time constants and volumes, and it may be due to the fact that they are shallow regions, deeper regions, but they may actually be different regions, and our eyes are open to both. The take-home point from this section is these are complex materials. Water's not as simple as it appears, neither is the palladium. And in order to get the active excess energy out, you must alloy the group 8 metal, whether it be palladium or nickel, with the protons or deuterons to very high levels of loading to get the successful cold fusion. Any questions?
Yes. Actually, your use of the word alloy in connection with loading of hydrogen or deuterium is reflected only in a small amount of literature. I mean, people mostly think of them as metal hydrides, metal deuterides, and alloys tend to be reserved for metal and metal being mixed together or something like that. So, metal hydride, better term.
But
Okay.
I think actually hydrogen there is in level 4. I mean, it's not 100% established, but I think it's almost there.
It's mostly hydrogen. It's got the proton, it's got the electron, it's sleeping about. It's got additional electrons from bands from otherwise. But I mean, in palladium, because the electron that's used well, we thinking of it as interstitial hydrogen and not as hydrogen metal.
So you're saying basically there's no lattice of hydrogen, even small fragments of.
Well, hydrogen occurs in palladium dihedral sites, which forms a sublattice, but there's very little in the way of hydrogen. Well, there's some hydrogen interactions.
That makes an alloy. There are even small fragments of crystal. I mean, say 2.3 by 4. I mean, semantics. I agree.
It's just usage in the literature. It's all.
Okay.
Well, it depends on the literature. In the chemistry literature, it's regarded as an alloy. In the electrical engineering, potato, at least we're on the same page, right? So let's go to the next one. Yes?
And as I'm reviewing the literature, my background is limited here, I hear a lot of people proposing that possibly the reactions are taking place in cracks or emerging from cracks in the material, and you're suggesting that as the material's loaded, we don't want it to crack. Is that consistent, or is that, I'm just curious of the contradiction of some of the things that are being talked about.
The active site is probably vacancies and not cracks within the loaded palladium. The cracks, as we have found, shut off the reactions. And I think if you want to look to see if they occur there, you're welcome to. But those who do experimentally, what we find is if you produce the cracks, you change, in fact, the kinds of bubbles that you see. You go from small bubbles over a tiny area, which I'll show you in a bit, to large bubbles coming out of the crack, and the excess heat goes away. And I challenge any of the people who say it's in the cracks to come show a demo. Yes?
When you do the accounting for all the energy inputs and outputs, don't you have to account for the energy that's required to take that 1 in 6,000 deuterium or heavy water molecules out of water and get it to a concentration that's useful?
Probably. We start, in fact, with low paramagnetic heavy water to begin with. And but I suppose if you wanted to do the full accounting, you would need that in the denominator. But it's still, you're dealing with a nuclear reaction in the numerator and a series of chemical and distillation reactions in the denominator. It's a very large number. But you're right. To be accurate, you do have to include it. And you also have to include, as I'll show you shortly, in the denominator, the energy for loading. Okay, so let's move on to that. We're going to talk about methods of measurements of excess power and excess energy in cold fusion systems. Now first, let's get some definitions. We talk about a fusor, and I'll show you a picture of a fusor in a bit. That is a wound cathode, which we wound into a spiral, and it turns out it's a metamaterial, and I'll explain what that means in a few minutes. A NANR is a dry cold fusion cathode that we have made out of zirconium and other metals, along with the palladium and deuterium, that is pre-activated. OMA control. There's a lot of people in the field who say we don't have any need for controls. I hope one of the take-home points after you see this talk is we use a lot of controls, and hopefully you'll help us invent more. Because I think the more controls we have, the less chance we have of being tricked by a false positive, most of which we've ruled out now. Excess energy is the net difference between the energy output and what we put in. Okay, that's what we're looking for here. So, how do we determine it? In the best systems that we use isoparabolic calorimetry. And that means that we have two wires going into our heat source. We're going to call the entire cold fusion cell the heat source. And we're going to treat it as a two-terminal device So we have essentially a DC current going in, a voltage across it. Therefore, we can calculate the power as voltage times current, and the energy is voltage times current integrated over time. Now, what about the energy out? Well, it turns out in our systems, what we try to do is make it relatively adiabatic. And that means that the heat is kept within, the temperature rises, but we also calculate for the heat flow that eventually leaves. So we're going to see there's two terms. One term comes from the rise of the temperature, and the other term comes from at equilibrium, the heat flow coming out. And we use multiple ring calorimetry because that way we check on the inside. We measure the heat across here, the heat across here, the heat across here, and we use multiple ways. Yes.
As you know, Mitchell, we've talked for a few years, and I'm not as scientifically knowledgeable as the rest of the audience. The term excess heat or excess energy has always bothered me, because in my mind, you put a certain amount of energy in, if you get more than that out, somehow there has to be a definition of something else changed, the mass of something decreased, or something, I don't know enough about it. So if those two terms are accompanied by some other measure that indicates where that excess energy may have come from, then to me as a layman it becomes credible. What I've been trying to wrestle with is, do we lose a deuterium atom? Or does something else occur that you could say that is the source of the excess energy?
You weren't here for 4 days last week, and it shows. So
Can I get a C minus instead of?
we all pass. All of you
Sorry,
pass.
never mind. Don't go back if you've covered it. I hadn't realized.
We'll get to it. The fact is as I will show you,
Yeah.
and as we showed last week, we are getting the excess energy from a conversion of the deuterium to helium-4.
Beautiful.
It's a very tiny change in mass,
Yeah.
but when we multiply that by c squared and the number of them, we find that it takes approximately 10 to the 11th to 10 to the 12th de novo helium-4 to form for every joule that we create. Okay. What I want to talk about right now is just how we measure the heat, and then we'll come back to that. Good question. So the power gain is equal to the observed output power over the input power. And one thing we do different from most of the other people in the field is we do not include the thermoneutral potential, which I regard as a fudge factor. And so we calculate the excess power by using a denominator of voltage times current, the classical way in electrical engineering of determining power. Now, what's done in chemistry is they take the current and multiply it by voltage minus the thermoneutral potential. So the fact is, what I show you today, if they're right, will be a lower limit to what we get. Yes.
Mitchell, in other people's experiments, the cell voltage is like 4.5, 5, 6, 9 volts. So the thermoneutral potential is like 1.5 volts. So you can improve the accuracy when you're working with voltage. Your voltage is much higher.
Correct.
So throwing away the thermoneutral potential has a much smaller impact on your system.
That's true, but we throw it away anyway. And the fact is, the corollary of what you say, Peter, is that for those that do drive it at low voltage, like 4 or 5 volts, it's a big fudge factor in the denominator. So we don't use it. We define the input electrical power as V times I, no thermoneutral potential, potential correction, and we use the time integral, yada yada. So we can then measure the excess energy, Joe, as the time integral of the output power minus the input power. This is classical electrical engineering. And how good do we do it? Well, our voltage accuracies are here. Our current accuracies are here. We often measure, well, we used to measure at least at 1 hertz. Now we're measuring so many things, we're down to about 0.2 hertz. But that's because we find that we have to get a really good measurement to 24 bits. Sometimes we have to take 700 milliseconds to measure it. And that's why we're having our Nyquist sampling rate drop to 1/5 of a hertz as opposed to that. You're going to see we drive these samples between nanoamperes and fractions of an ampere per square centimeter. And many of the devices that I'll show you have 4 terminals on the cathode, because I'm also interested in measuring the conductivity of the cathode through it. And we'll come to why we do that. So our data acquisition is at least 24 bits now. There's our sampling. And the other thing we do is noise measurement over long amounts of time so we can rule out false positives. And I'll show you how we do that in a second. This is one of our old setups. It's certainly gotten easier. These are current sources that we use to drive it, electrometers we use to measure it so we don't tap off. We're more accurate. This is a temperature-controlled unit, and we did an irradiation experiment we'll talk about later. And just some pictures of the lab. This is our driver. One of the things we have found over the years is, let me use an analogy for these devices, is the baseball stadium. The calorimeter is the baseball stadium. The cold fusion device is the batter. And what we have built is a series of devices that drive it. And it turns out that, especially with the nanors, the dry cold fusion devices, to be incredibly important, because the input impedance can change between 100 gigohms and a kilo. So we have a batter, the batter is between the pitcher and the catcher, which is this device for the fusor. This was the 10K driver that we showed back in 2003 when we first did the first demo. And what we do is we often measure at multiple points within the system. Here around the fusor we have 4 points. And the other thing that's important is we do a lot of control. So we'll do a water control, an ohmic control. One thing we do not do is flow calorimetry. And I will just briefly tell you why. It has to do with your coffee. Bernard instability is such that a hot solution is less dense than a cold solution, will rise to the top. And one of the things we early discovered is when we do cold fusion measurements, as I reported back in 1993, we don't use thermistors because they're time variant. We like thermocouples, we like RTDs. We also don't like flow calorimetry, because flow calorimetry in low flow systems can give a false positive if it's vertical. For example, the Patterson beads, when they first came out, they were using horizontal flow. They were getting 3/4 of a watt excess energy, 3/4 of a watt excess power, which is very impressive. If they did it vertically at low flow, they got a pseudo kilowatt. Now, to me, if you change the flow, you're not changing the output of the device. And therefore, we like something that doesn't change from that. Okay, so how do we do it? What we do is, as I showed you, we are looking at a near adiabatic system, an isoparabolic calorimetry, where we are looking at a temperature rise, and I'll show you that. We're looking at the heat flow out. Has to take account specific and latent heats. Has to take into account the thermal conductivity. We can go back over the, we just don't have enough time to go over this. I apologize. In only 2 days, we're going to cover a lot of topics very quickly. And Jet Energy is thinking of having an advanced course later in this year, which will run a week or two, and we can go over more of this for those that are interested. This was the first isoparabolic calorimetry using an ice calorimeter, which is now becoming of much more interest. Although, when you measure heat flow, you can do it in one or more directions. We try to make most of our measurements in a single direction to make it easy. I'm going to skip over all of this. The other thing that's interesting is when you measure heat flow, what's often done is to do the difference in temperature between the two. That's the odd term. What's interesting is, what's often left off is there's an even term too if you do the calculation. And we published a paper, this is Fleischmann's calculation. I think ours is a little better. And when you add the additional term, you get the following. This is let's see, this is what we're looking at time is going in the x-axis. We're looking at power in the vertical axis between 0 and 2 watts. So here's our input, these broken lines. And it turns out when we try to recover what it actually is, if we just use Newton's terms, with the odd term we get this, and when we add the even term we get this. So we always use the even term now as well. The other thing we do is we try to get a long measurement where nothing happens. See here, we're looking at time over 15 hours into a cold fusion device. And we're looking at temperature between 25 and, I guess it comes up to 85, 90 degrees. Being relatively poor for funding, the cost of low paramagnetic heavy water runs about $3,000 a liter. So I don't like burning it off. So we tend to clamp our systems, at least in the past, up at about 90 to 95 degrees centigrade. So that's the only reason you're going to see these systems stop there. Now there's a much greater interest in going higher because of Carnot efficiency, and we'll come to that later. So here, for example, we see inputs and outputs. Here's our controls. Here's the cold fusion device. And by measuring here over a long time, we're able to do noise measurement. Now, why is that important? For the following. Here again is our time measurement going in x-axis. Here we see log power in watts going between, this is 10 milliwatts up to 100 watts here. And we're using various drives. And when we drive within the noise level, we get a false positive. So we now always make sure that we drive above the noise level. And that's why we do the noise measurement. Okay. Another thing we do to assure ourselves that we are really measuring excess heat is that we do redundant measurements. We'll do time integration. I showed you the thermal waveform reconstruction. Let's go back. That's really important. I want to see that if we put a square wave into the control, we use an ohmic control like a half-watt resistor to make sure that our system works. I want to make sure that if I put a square wave into the control, we get a square wave out. Otherwise, you can't believe your calorimeter. Okay, so that's thermal waveform reconstruction. The redundant calibrations that we use, the multi-ring calorimetry, we have augmented using the measurements that I'll be showing you with heat flow sensors. In addition, we'll use paired Stirling engines. I'll show you those where we'll put one Stirling engine over the ohmic control, one Stirling engine over the cold fusion device. We do near infrared sensors. We've also done paired electricity generation, where we will put a thermoelectric conversion device over the ohmic control and one over the cold fusion device. So we try to use multiple methods to show that we really do have excess energy. And finally, in addition to the thermal controls, which I really recommend you use if you go into this, here's two more that we use. A dual ohmic control is where we build two complete calorimeters. Because a calorimeter might be affected by changes within the room, but if you have two identical ones next to each other, one with the ohmic control, another one with the cold fusion device, we'll put an additional ohmic control within the cold fusion device, but we've now normalized for the calorimetry as well. And finally, we do metallic cathodic controls, where we do inactive materials that don't load, like iron and aluminum, and those never give excess energy. And so we have chemical controls, ohmic controls, and then what we try to do is have the heat go from the core through the heat sensors. We'll do the time integration. We'll put it into, for example, the Stirling engine that I'll show you. And by the time we get done, we'll have up to 6 different methods of confirming that we're getting excess energy out. These are the dual ohmic control systems. And we first showed these at the demo in Peter's office at ICCF 10 when we showed the fusor. And there we were getting energy gains of 2.7. 270% beyond the input energy, and we did that for a whole week. And here, for example, these are in electrical series. You can see the platinum anode here, palladium cathode here. Well, this is before it was filled with heavy water, which we did in his office. Here's an ohmic control. And what we did is, so we have the same current going through both. We measure the voltage across each system. That's why we see the multiple voltmeters. And in fact, in Peter's office, we did dual voltmeters, just in case there was an error in one. And of course, there never is. But that we were able to show the power that was going into here, the power that was going into here, and this one had a higher temperature. Clear, unimpeachable proof of excess energy coming out with less power going in. Okay, take-home points. If you want to improve your analysis, avoid flawed calorimetry. I'd avoid low flow, vertical positional flow calorimetry. Make noise measurements so you make sure that you're driving the system above the noise of the system. And we have a paper here. I brought a series of papers for people who are interested that we published on this. And this one you might want to check, Patterns of Failure in Cold Fusion Systems, where we go through and talk about where we think several people in the field might have amplified what they really got. Do your analytical calculations and control. You can't do enough controls. You should do an ohmic control, a water control. You should do an inert metal control. And as I say, if you can afford it, do a dual calorimetry control. And voila, if you do it, you get super data. So for example, this. Now what we're looking at here, if we get done, if you can look at these curves and recognize what's going on when we're done, then I'll regard this as a great session. The purpose here is to teach you pattern recognition. And so I'm going to take a couple of minutes showing you what's going on here. Here we have time. Here we have, on this axis, power. This axis is energy. And what we have here is a dual calorimetry system, as well as having an ohmic control in each one. So here, we're looking at the power in to the ohmic control resistor and the power out. Nice match. See that? Nice match. Now, if it was a perfect run, these blue and green lines would be right in between here, but nothing's always perfect. Yeah.
Is that minutes or the time axis is minutes, hours?
This is probably minutes in this one. And this is a cold fusion fusor that we had prepared initially. Peter has already taught you the active region within the palladium. He's taught you how the vacancies are a big role in the active cold fusion device and how they diffuse in, because once the system is loaded, the energy is improved for these vacancies to come in by about 30 or 40 milli EV, and over the course of about 150 hours they diffuse in. Once it diffuses in, we have a system here where we can turn it on quickly. So this is not ab initio. This is a system that's been prepared and ready, but when it is ready, here's what we see. Here we put into the cold fusion devices here, and here is our output. So we get increased power out, and if we time integrate it, which are these straight lines, we get increased energy out. Okay, let's spend a couple of seconds here making sure we understand that. Time is this way. These two are a match, showing that what we're putting into the ohmic control we're getting out for energy. There is no energy gain for the ohmic control. On the other hand, the cold fusion device gets this much energy increased out, because here is our increased power as a function of time, and when we integrate it, we get this. And also, we can see heat after death. Here we turn off our input, and although the ohmic control device comes down quickly, the palladium itself still is making these helium-4. So we see what Fleischmann and Pons, I don't like the term, but they call it heat after death, because when they ran their system, it ran out of heavy water, and yet it kept making excess energy. So that term is stuck, heat after death. And we call this tardive active. Well, we'll come to it in a second. Any questions?